It's my pleasure to be here today introducing Shashwat. I think he's one of those authors that when you read with detail, you learn to trust in his ability to be critical and to have come up with the different edge cases that sometimes out of papers really don't think about, right? So he's one of those people that you can really read and have this trust that the work that he did was actually what is written down and not some spurious correlation or shortcut that no one can anticipate, and then all of the conclusions and experiments are somehow wrong. So I think that if you pay enough attention, and especially if you talk to him afterwards, you will all realize that he's an author that is worth reading and that this work is probably very important to all of us. So without further ado, please welcome Shashwat.
Thank you so much for that generous introduction. And thank you, Johannes, for inviting me for giving this talk. So I'll talk about our work that we released recently called FutureSim. The goal of this work was to essentially evaluate adaptive agents. So we have these like language model agents that are starting to do like really cool things, especially with like coding, but we wanted to see, are they like two questions. One, how good are they at like modeling real world dynamics and like social dynamics? And the second, can they like adapt to new information as it arrives over time in the real world, just like humans do all the time? So this is joint work with some excellent collaborators across Tübingen and Stuttgart. And this is also work that we'll be presenting at ICML. So if you have any feedback on the talk or the work, I would just love to hear from you. So I think the core premise of this work, and I want to convince you about this because I think it's like even more important zooming out from this work itself, is that I think continual learning is something that's like gaining a lot of popularity right now. It has been a buzzword for the last decade or so, maybe even longer. And I think like one important thing that a lot of continual learning literature misses and like has problems with is the fact that you really need realistic environments to study continual learning. And this is like, I think, uniquely important. Obviously, you need realistic environments everywhere, and realistic environments are better than like not realistic environments. But I think for specifically continual learning, I think this is like particularly important. And I think there are three reasons for which essentially bring us to this claim. So I think the first thing is something that most people should agree on, that you can't remember every single detail if you have finite memory. The second one is that as humans, at least, we learn what to remember and what to forget implicitly. So in some sense, something in our brain is telling us that these things are important and these details can be forgotten. And it is possible that this, whatever intuition we have internally to like decide what to remember and what to forget, this could be environment specific. So it could be tailored towards how things happen in our world. And it could be tailored to how learning and forgetting happen over time in our world. It's not like we are thrown things at completely random order and then we have to remember like this random order of events. There is like a chronology to how events happen in the world and how the world changes. And in some sense, this task of learning what to remember and forget, I think, is based on like we're internally learning some predictions of what information we will need in the future. And this is the stuff that we're remembering. And it is important to point out what is not realistic. And I think like there are a lot of settings that people study continual learning in which are unrealistic in many ways. I won't go into detail here, but there are like, here I have like some examples. For example, just fine-tuning once is not exactly fully continual learning. Training on completely disjoint tasks is not exactly what I do in my day-to-day. A lot of people take IID samples and then just order them sequentially and try to learn IID samples sequentially. I also think this is not exactly what human continual learning is like, because there is some connectivity in how things progress. And also like simulations, sometimes people design simulations which are more temporal and like capture these aspects, but also they're not based on real data. They're like either some artificial program someone wrote up, and or they are like in some sense some LLM generated completely vibed environment, which also I think is like not realistic anymore. So so let me talk a bit about how we try to do this in this paper. I think this is not a perfect setup, but we can talk about some benefits of this and some drawbacks. So I think the key design choice here, first of all, we study this forecasting task. So the task is that models have, like we ask models questions about the future. So for example, who would win the Super Bowl, or who would be the next Nepal prime minister in the upcoming Nepal elections. And we are studying language models in this paper. So language models have this knowledge cutoff when they are released. This could be like a few months before today. So what you can do is you can create these questions from events that have happened in the last few months and pose them as forecasting questions to language models. This is something that we've worked on. Like, this is derived from some work we've done over the last year. And once you have these questions and answer pairs, you can pose them to the language model and ask it to make predictions. But more interestingly, what you can also do is, instead of just this single one-time question answering task of, here's a question, give me the answer, you can also ask the model to adapt its predictions over time. And how do you do this? How does the model adapt? Like, what new information does it get? What we try to do is we take real-world news articles and we basically simulate how new news arrives every day in the world. And again, all of this is drawn from the world. So we literally downloaded news articles from the internet, and we replay this simulation from January 1, 2026 to March 28, 2026. And every day new news articles become available to the model. It can update its past predictions. And another continual learning signal that comes is that as we get to know the ground truth, or as the world got to know the ground truth of each of these questions, for example, on January 21st, it became known who the new TikTok CEO was in the US. And as this information arrives, we put this in the set of questions that the model can view and interact with, so that it can also learn from how its past predictions were wrong or correct. And it keeps doing this interactively, these things interactively, where it views the tasks, learns from resolutions, searches for new context, submits some predictions, and this keeps going on for the entirety of the simulation. So just to give a qualitative example, we also compare to prediction markets, which is, I don't know if you've heard of prediction markets, but here I have this example from Polymarket, where these are these platforms where humans go and make predictions and do exactly the same task in a way. And we also look at new news, and based on that update our predictions. And people on these platforms are doing this. They're making, I think, for example, on this particular question that I'm visualizing, $2 million of real money were traded. On some other questions that we have in our data set, which happen to be parallel to prediction markets. The Super Bowl prediction market had $700 million traded. So, I mean, in some sense, this is also an economically valuable task to track model performance in. And what we show here is that actually, if we visualize how GPT 5.5 reacted to new news becoming available in the environment, it actually has a trajectory that looks quite similar to the prediction market, I think. For example, when we see this uptick in the blue part, where the prediction market suddenly becomes very confident in the actual ground truth answer, which happened to be, I think, Balendra Shah for the Nepal prime minister election. We also see GPT 5.5 has these upticks, and we see, we can look at the qualitative traces and see that it finds news articles which are hinting at this guy might have a better chance at winning now. So in some sense, we're looking at how models can use a large context repository to update their predictions over time. And we track, we have this other side where we track this over many different markets. In some markets, we even see that GPT 5.5 leads the market, which is that actually, if you only traded on that market with GPT 5.5, for example, in the Super Bowl market, you could have actually made a lot of money. So so essentially, to quickly summarize why we are studying this setting before I get to the results, in the setting, there's a chronological order. So things happen over time realistically as they happen in the world. All the events are real. And also, crucially, the model can't shove every single piece of news into its context, because models have a 1 million or 10 million context. And actually, we have 50 million news articles in our news repository here. So the model actually has to use search tools just like a human would to fetch relevant pieces of information. And another crucial design choice is that we don't tell the model, update this question right now. Instead, we just let the model decide which questions to update its predictions on its own. So there is a question CSV that the model can interact with, and it can decide which questions to do research for and which questions to actually submit new predictions for over the course of the simulation. You could also say this is sort of a subset of the world modeling task, where you are trying to predict how the world evolves over time. And the model predictions are probabilistic, so we ask it to report a distribution over probabilities, which also tests for calibration in some way. And like I mentioned, this is an economically valuable task because a lot of decisions we make, or enterprises make, or governments make are based on such forecasts. So this is a quick view of the current leaderboard. We keep testing new frontier models as they come out. We keep reporting the results. So immediately, one thing you would notice is Fable 5 is at the top. And I want to caveat this result by saying that Fable 5, the knowledge cutoff, it it is trained on some January data, so we should not fully trust the Fable 5 predictions, but I left it there just because we did test it. But if we ignore that data point as well, we see that GPT 5.5 seems to be doing quite well, better than Opus 4.7. And what's interesting is that GPT 5.5 and Opus start at the same point, roughly. If you look at the leftmost part of the plot, which is like 15% accuracy. But crucially, GPT 5.5 adapts a lot better to new information as it comes and becomes much better than Opus over time. And and the open weight models seem to be like lagging behind significantly on these kind of tasks, which somewhat makes sense given that their priorities right now are like catching up on code and other agentic tasks like that. So to zoom in a bit on the specific properties we think the setting studies, for which we can like run some ablations because we are essentially doing like a backtest simulation. So for example, like if you want to study how do different models specifically differ in their ability to adapt at test time, one thing we can do is we can start them at the same set of predictions. So in this plot, we started all the models at Qwen 3.6 plus predictions, which was the worst model in our leaderboard. And then we saw how good the models were at adapting over time. So ideally, what you would want is that the models just, each of the models goes back to their original top point. So for example, like all of them, I didn't show you the Brier skill score plot earlier, but GPT 5.5, for example, has like a significantly positive Brier skill score. It's like around 0.1 in this setting. But once we started at bad predictions, we see that it can't even recover to 0. And one thing to note about this metric here is that 0 is actually the point where if you predict nothing, you get 0. So basically the model's predictions, once you start them at a bad point, they're not able to adapt them to even positive information in a way. Like they get stuck at the initial predictions and they don't adapt enough. We can also zoom in on the subset of questions where models actually make updates. So obviously models don't make updates on every question when we start the simulation with like an initial set of predictions. And then like the rankings change a bit. GPT 5.5 and Opus are a bit better than DeepSeek then. And crucially, we also like ablated if we don't give the model access to any memory being like file system read writes or like notes that the models can take. I can show you a trajectory later on what notes the models actually take. We see that all of the models, like the dashed lines are without memory and the solid lines are with memory. And clearly when you remove memory, models like perform worse. In fact, some of them even start worsening because they keep increasing confidence in their old predictions. The other important capability this tracks is, like I mentioned, there's like partial observability over the context. So the model has to use search tools to actually pull out relevant information. And we do find that search is like extremely important. So for example, if we and especially like when I say search, I mean like adaptive test time search. So the idea is that you need to keep making like refining your search queries and pulling out new knowledge. And we actually ablate these a bunch of times. So for example, we ablate if we don't give the model agentic search and instead only give it like a single search query, then we see that the performance drops a lot, which shows the importance of having this agentic search. And also we show that if we don't update the context over time in the environment, like we don't add news articles, the model is not able to improve even if we rerun the full simulation. So in some sense, having access to this new information and using this new information is really important for the capability that the model gets to in the end. And another thing is like we also vary the amount of reasoning effort the model uses. This is for GPT 5.5. And again, you can see that, so the darker lines are ones with higher reasoning efforts because GPT 5.5 allows you to set like 5 different reasoning modes. And you can see that there is like a clear benefit from doing like more reasoning and more interaction with the environment. So more inference compute helps you do better at like this task. And finally, this is the last result I'll show, which is that we were just curious what happens if you let multiple copies of the same agent run in this environment, sort of like a self-play setting. And in this case, the agents only have access to the aggregate prediction that is there in some sense in the market, you could say. So they can look at the mean prediction across all agents and use that to like get some information and maybe use that information to update their forecasts. And what we do see is that like we ran this with DeepSeek V4 Pro. And what we do see is that there is this interesting trend where like on the y-axis, we essentially plot TB distance, which means that if it increases, the predictions are getting more dissimilar. And if it decreases, it means the predictions are getting similar. So in the single agent runs, which are the blue lines, the agent's predictions diverge over time. Whereas in the multi-agent run, where they are all running in a shared environment, their predictions converge towards each other over time, which is interesting because it tells us something about what's the default propensity of these agents. Are they like do they resort to groupthink if given access to multiple agents in the same environment rather than maintaining their diversity? Yeah, that was my talk. Happy to take any questions. We do release like a bunch of materials, and this is obviously like a larger project we're doing called like Open Forecaster, where I can show you that we have like these. Yeah, so we've been doing like a bunch of these projects. So this is like the third project that we've done in this line of work. And we're actively continuing to work on this. So also very happy to chat if someone is interested in collaborating or talking about any of the other papers that we did. And yeah, and then we release our data code. We also have like this nice visualization that I want to talk about because I just finished making this, where we plot like each agent trajectory. So you can go and look at how the agents behave, what nodes do they take in their memory, and how this evolves over time across model runs. So there's like a bunch of interesting things going on here. Yeah, yeah, happy to take any questions.